All right. Well, thank you. It's a pleasure to be here with all of you today. Devin, thank you for the introduction. And as you mentioned, I'm interruptible. We have a lot of material to cover, so I'm going to move quickly, but the point is your understanding. So if you're confused or if I need to explain something better, please stop me and let's address it. So the talk today is going to be about semantic search and neural information retrieval. What is it? What can it do beyond a standard keyword search? What are some of the architectures that are employed for this kind of search? So before I get into the details there, let me give you a quick background on myself. I've been a software engineer for about 20 years, 10 of those at Google, 8 of them I was in Google Research. And then the last 4 years from 16 to 20, I was leading research into neural information retrieval at Google using neural networks. So I was involved in all aspects of designing the neural networks for large-scale information retrieval. But as an engineer, I'm very interested in not publishing papers so much as in building systems that people can use. So all of the auxiliary machine learning that sits before and after the neural networks in the information retrieval pipeline, I have experience working and designing that. So for instance, statistical calibration and re-ranking. We'll talk about all of that briefly today. And then also I'm very interested in how do you actually deploy one of these systems to production. Neural networks, for those of you who are familiar, are notoriously computationally intensive. And so, you have to pay careful attention if you want to be able to scale up to 10,000 or 100,000 documents and doing retrieval over that. Okay. So I'm going to move along kind of quickly, but I think it makes sense to let's say first start with what does semantic search even mean? It's had many meanings over the decades, and I mean something very specific. The word semantic itself in English just simply means of or related to meaning in language. So a semantic search, in a way, not very descriptive, a keyword search is a semantic search. It captures some aspect of meaning in a language, or else it wouldn't be useful. So specifically in this talk, semantic search refers to doing information retrieval with neural networks using techniques that didn't exist before 2017. So this is all very new. This is cutting edge. This is not widely deployed outside of, I would say, the FANG companies. And these neural networks are able to understand language at a much deeper level in a more human-like way, I would say, compared to a keyword search. So to motivate this discussion, I'm going to quickly step you through how a keyword search operates. Let's say that I'm running this search for dog adoptions in Silicon Valley, and I have this big data set of thousands of documents, and those are portrayed down at the bottom. And one of the first things I want to do is look at which words in the query show up in which documents. Okay, so different words show up in different documents, and then of course there's some words like the word in that show up in almost every document. And we would say that that has very low information content. So in a traditional keyword retrieval pipeline, words like in tend to be stripped out. That's called stop word removal. And it's automatically configured in systems like Solr or cloud platforms like Elasticsearch and Algolia. And then of course, when I'm searching for adoptions, I also want to match adoption, adopted, adopting, all of the variations and conjugates of that word. So I need to strip the words down to some base form before I run the search, some kind of normalization that's called stemming. So it's a language specific step that's done. And again, it's provided out of the box. So now I have, dog, adopt, Silicon Valley, and I'm going to match these terms. Okay, and I need to match these terms fundamentally based on something that correlates to what's in statistical terms known as the mutual information between the terms and the documents. So that is captured in algorithms like TF-IDF and BM25, which are used for keyword retrieval. Their scores essentially correlate in some way to the mutual information between these terms and the documents. Okay, so let me stop there. That's what you get out of the box with a keyword search. But in order for the keyword search to really be intelligent, I would want to be able to do something like searching for bulldogs for adoption in Cupertino and match that. That would be really intelligent. So how do I get that with a keyword search? To do that is more tricky, and it requires something called term expansion, where I need to go in and basically define essentially that, for a dog, here are the types of dogs. These are things that are dogs: bulldog, chow chow, beagle, collie. Similarly, Silicon Valley is actually San Jose, Mountain View, Sunnyvale, and Cupertino. And then I can generate a much larger set of queries. Essentially, I rewrite this original query into a whole set of queries, and running these against my document store, I can pull back a much richer set of results. And so now I finally kind of achieved my objective of being able to search for, dog adoption in Silicon Valley and finding a bulldog that's up for adoption in Cupertino. Now, this is the point where the search looks, pretty impressive and it seems intelligent. The problem is that term expansion is not something that's available out of the box with a keyword system. These term lists have to be defined, and then they have to be maintained. And no sooner, unfortunately, do you define these term lists, then the exceptions start to pop up everywhere. So let me just give you an example that now if I've got this nice term list that expands the word dog, and now someone enters this query, good hot dogs in Silicon Valley, I think it should be obvious that expanding dogs in this query isn't a good idea. It's not the same kind of a dog. So you have all of these corner cases showing up because of the flexibility of language. This is not a problem for humans to understand, but keyword systems really struggle with this. And the end result is that until now, sophisticated search systems, which rely on keyword search in the back end, have remained the domain of companies like Google and Bing, which have multi-billion-dollar budgets to maintain these systems and keep them running optimally. So for instance, when I was at Google, there was actually a team of engineers dedicated to this problem of keyword and term expansion in the queries and finding the edge cases and fixing the edge cases, and new ones would keep coming up. So roughly speaking, we have this graph that as you try to improve the search result quality linearly, the cost and complexity of that search, both in terms of developing it and then maintaining it, deploying and maintaining it, go up exponentially. All right, so that's a little bit about keyword search, okay? And let me now pause, and I'm going to show you a demo of what a neural network-based search can do, because it really levels the playing field between smaller players who have search problems they need to solve but don't have the budgets to do it, and then the large companies like the Googles and the Microsofts of the world. So I'm going to go over to the demo. We've taken a router from Amazon, which is very popular. It's a Netgear Nighthawk router. We took about 2,000 reviews and uploaded them into a semantic search system. This happens to be, the Zero Semantic Search, my company's platform. And I'm just going to put a query in here. Can I stop my child from using the internet? I'm a parent. Maybe I'm worried about this, right? And now what you see is a list of results coming back. And within the results, our system is actually able to identify with machine learning the most relevant part of the review. Okay, and so you see, I like being able to disable the internet when my son plays video games. So it didn't say child, but it said son. Okay, and that's semantically similar. So the system was still able to return that. There's no way to block social and time-wasting sites at night for your children's devices. So here you've got, no explicit mention of the internet, but social time-wasting sites, it's clearly, we're talking about the internet here, right? So that's the kind of intelligence that I'm basically getting for free. I didn't need a whole team of data scientists to define these term expansions and maintain these lists for me. I'm getting it for free here, and it's a much more sophisticated experience. One of the other interesting things that you can do with a neural search is, if you've trained the neural network correctly, you can actually work across languages. So I'm just going to show you a real quick example. If I go to Google Translate, I'm going to ask, can I get signal outside? Maybe that's a question I've got about this router. Okay, and I just translate to Chinese. I assume this is a decent Chinese translation, and I'm going to put it in here. And here it is. Because of the way these neural networks work, people, when they see this, they ask me, oh, did you go to Google Translate and translate to English and run the query? No. This is actually the neural network directly interpreting the Chinese and returning the most relevant results it can, even though those results happen to be in English. All right. So there's the demo. Hopefully you get a sense of what you can do with a neural retrieval system that you couldn't do with a keyword system easily. I'm going to go back into the presentation and give you a bit of historical overview now on the 2010s and NLP, because this was a watershed decade for natural language understanding with computers. We entered the decade, computers were struggling to understand language at the level of a 3-year-old. And as we're leaving the decade, by around 2018, computers were matching the performance of graduate students on question answering data sets from Stanford University. So there's been an enormous change, and I want to share my perspective on the 3 key breakthroughs in the past decade that have brought computer and machine comprehension of natural language up to a human level. Okay, so I'm going to go quickly, but please stop me if you have any questions. Okay, so neural networks require numeric input to operate. So you've got to turn the words in your language into numbers somehow. The way this was traditionally done was with what's called a one-hot vectors. The way one-hot vectors work is like this. You're going to take, let's say, the 50,000 most common words in the English language, okay, and you're going to have 50,000 dimensional vectors. You're going to assign every word an ID, okay, and then in that position of the vector, there's going to be the value 1, and everywhere else is going to be 0. So let's say that King has ID 17. In position 17, there's going to be a 1, and everywhere else there's a 0. And here in this example, Queen has ID 2. So it's got a 1 in position 2 and a 0 everywhere else. This is how words were fed to neural networks, and neural networks were never able to make much progress on language understanding with this paradigm. And one of the reasons for that is because there's really no connection between one word and another. King and queen are semantically connected, but they're no closer together in the vector space than any 2 randomly chosen words, if I'm using this kind of a scheme. So the first breakthrough happened in 2013 with word vectors. Word vectors provide dense embeddings. So you're talking now about vectors between 50 to 300 dimensions, all non-zero entries. And crucially, the geometric structure of the vectors and the relationship of the vectors to one another reflects the semantics of the words themselves. Also, just as crucially, the procedure for training word vectors is unsupervised. So for instance, you can feed Project Gutenberg, all the works of Project Gutenberg to this algorithm, and you're going to get vectors for every word in the English language as an output. And then, looking at the diagram on the right there, going back to the king and queen example, now we have word vectors, and you can see that the 2 red dots there represent king and queen in this word vector space, okay? And they're much closer together than 2 randomly chosen points on the sphere. Okay, so that's the idea of word vectors. And this concept of vectorizing the meaning, turning the meaning into a vector in a vector space, this can be extended beyond individual words to sentences, paragraphs, even to full documents. Okay, and this is one of the key foundations of modern neural information retrieval. All right. So moving on, the next breakthrough came in 2017. Language is fundamentally a one-dimensional sequence that we receive this one-dimensional stream of words, and we construct meaning out of it in our minds. The way that one-dimensional sequential information is handled in neural networks traditionally was with recurrent neural networks. A recurrent neural network at time t takes some input and also takes its output at time t minus 1 to produce the next output. So they're able to model sequences of information. So until 2017 and the introduction of transformers, systems like LSTMs, for those of you who are familiar, were dominant. But the problem is that these kinds of systems are very difficult to train. They're slow to train, they're difficult to train, they're very difficult to productionize. So transformers brought the benefits of sequential modeling into the paradigm of feed-forward neural networks. Feed-forward neural networks are much more scalable. They're easier to run in a production setting, and you can train them much bigger. So now feed-forward neural networks for the first time gain this ability to consider sequential information. So man kills bull now looks very different than bull kills man. Okay, and I can't overstate how critical transformers have been to the field of deep learning in general, whether it be image processing, video processing, or anything else. However, nowhere was the improvement more drastic than in the field of language understanding. And that is because human language is fundamentally sequential. So about 10 months before Transformers came out, I had embarked on leading this team on large-scale information retrieval with neural networks. When Transformers were released by Google Research, we were one of the first teams to incorporate them into our system. And that one change alone gave us a 27% relative jump in F1 score. So anyone on the call who knows about data science, F1 score is the geometric mean of precision and recall. That is an enormous jump, and it especially coming from just a single change inside the neural network. Normally, you're talking about fractions of a percent improvement. I give credit to Transformers for allowing us to launch Google Talk to Books. It's an AI experiment from Google. You can actually try it out yourself. You search 200,000 books with neural networks. I actually trained those neural networks to power the system. We couldn't have launched, or we would have launched something much weaker if it hadn't been for Transformers. So that was the next big breakthrough in 2017. And then the last big idea became popularized in 2018, a system called BERT. If anyone follows NLP, I guess you might have heard of this. So BERT introduced the idea of unsupervised pre-training. You see, think about humans and language. If you're going to ask me about medical topics, okay, I understand the English language. I'm not a doctor. I'm not an expert, but you could hand me a few medical papers. And if I read them, I might be able to get some idea of what they're talking about and be able to have some kind of a discussion with you on the topic afterwards. I don't have to learn everything from scratch every time. I carry my knowledge of language around with me. So essentially, the idea that BERT introduced, it's a very deep, 21-layer deep transformer neural network. They trained it ahead of time on this unsupervised task. Unsupervised is key because they essentially had unlimited amounts of training data then. And it's a kind of a fill in the blank task. So for instance, John bought eggs at the blank. Okay, store makes sense here. School probably doesn't make sense. The neural network has to predict and fill in the blanks. And over time, it gets better and better at that. And getting better on this task actually means understanding the mechanics of the language. Okay, the two are directly related. So you pre-train on this one generic task. And then what they found is that then with a very small amount of task-specific training data, the neural network can get very good very fast. So with only a few hundred examples on the task that you care about, now the neural network is able to perform almost at a human level. And so what they showed is that they took this one system and they were able to smash all the previous records over a wide range of language benchmarks. I think 15 or 16 different language benchmarks. They set new records. And crucially, it was the first time an AI system ever exceeded human level performance on the Stanford question answering data set, which I alluded to at the start of this talk. There was actually a New York Times article published about BERT. So this was, I would say, the third key moment or the key insight in the past decade. And BERT by itself, for all of its power, is not productionizable. It is extremely CPU intensive, and it provides an ON search. So if you want to search for the answer to a question in, let's say, 10 documents, it's kind of got to linearly scan through the 10 documents. So searching through 100,000 documents with a cross-attentional BERT type system, it's impossible. Okay. All right, so that was a quick recap there. I want to get into the actual architecture of a modern neural retrieval system next, but I'll pause if there's a question. Otherwise, I can move on.
Not seeing any questions, so you can move on.
All right. Okay, so let me go through what a modern pipeline looks like. These are the same stages that would be present in a traditional pipeline, but there are neural correlates to each of these. So I'm going to comment on that. When a query comes into a large-scale search system, generally there's several different backends that you might potentially hit depending on what the query is about. So you might have noticed when you search on Google, sometimes you get video results, sometimes shopping results, sometimes it's just plain web results, other times you might get flight results. It depends on what the query is. So determining the intent of the query and routing it to the appropriate search backends, that's what query routing refers to. This is done almost exclusively with deep neural networks these days. The next step is actual retrieval. So one of these backends has been selected. Now it receives the query. How is it going to search through thousands of documents to retrieve the most relevant set? So this is done actually in two ways in modern information retrieval systems, neural information retrieval systems. It's done surprisingly with BM25, keyword retrieval. And that's a popular choice because it scales very, very well. And then the other option is to do it directly with neural networks. And that's what our company focuses on. So we generate these vector embeddings that represent the documents. And we essentially generate a vector embedding of the query. And then we find the nearest documents to that query. And those tend to be good search results. So for that, you need a specialized piece of infrastructure called a vector database. There's several good ones out there, but if you're familiar, like there's from Facebook research, Annoy, HNS Live, all of those are out there as viable candidates for fast vector search. And that's an area of very active research at the moment, is how to scale those things up. So you've got two options over here. And then the next step is re-ranking. Okay, so re-ranking refers to two problems. If I have result sets from multiple search backends, how do I merge them into one final list? And then how do I reorder the entries in the list so that the best items come to the top? So commercial neural information retrieval platforms, which I'm going to cover in the next slide, some of them will use a BM25 search and then use re-ranking with neural networks, and that's why they are dubbed neural. And others will actually do the retrieval step directly with neural networks. And they both have some pros and cons, which we can discuss at the end if there's time. The next key step would be snippet extraction, particularly when you're doing something more sophisticated than matching keywords in the title of the document, like you saw in the demo. There's relevant information buried deep in the review. You need to be able to highlight what's relevant so that people know why you're showing them the search result. Otherwise, it's just going to be a bad experience. So some retrieval pipelines can actually do the snippet extraction automatically as a part of retrieval, and that happens to be the case in our system. In that case, it can actually be fed into the re-ranking step and produce an even better re-ranking. But in other cases, it can't be. And then snippet extraction is actually fairly expensive. So it needs to be done after re-ranking so you can limit to running on like the top 3 or top 10 documents, however many you're going to show on that first page of results. Okay, and then the last step is something a little bit more advanced. It's statistical calibration of the results. Whether it's BM25 or a neural network, you're going to get some kind of numeric score out of the system. Well, what does it mean to get a score of 26 from BM25 or a score of 0.73 from BERT? Especially 0.73 is deceptive. Is it 73% probability of correctness? Well, it turns out it's absolutely not. These deep models, deep neural networks in particular, are extremely uncalibrated. They tend to skew towards the extremes, 0.99 or 0.01, with very little gray area in between. For the sake of human interpretability of the results, you want to bring those scores into alignment so that they reflect the true likelihood that the answer being shown is relevant. So 0.7 should mean 70% chance of being relevant or a correct answer to the query. All right. So moving along, here's an overview of 3 commercial PaaS solutions on the market today and just how they compare to one another. So there's Kendra from Amazon, which was launched in 2020. Microsoft Semantic Search launched in 2021, I believe is still in beta. And then there's Semantic Search as well. Key point, the retrieval is done with BM25 in both Kendra and Microsoft Semantic Search. They use neural networks for re-ranking. One of the nice things about this approach is, again, it scales really well to very large data sets, and you kind of get an immediate boost over the performance of keyword search. On the other hand, doing a dense retrieval directly with neural networks has some advantages. You can pull back results from other languages, which by definition are not going to have any keyword overlap. And you can even pull back results from the same language, which have no keyword overlap. Our platform does not perform the re-ranking step. Our customers who want to re-rank and merge result sets from other systems implement the re-rankers themselves. Unfortunately, none of these systems perform calibration, but I imagine that's something that should be added in the future. All right. Any questions there? I'll pause. Otherwise, I'm going to kind of conclude with one more example that's not directly search, but should give you an idea of like the power of neural information retrieval and where else you could use it.
Yeah, I'm looking for people typing, but I'm not seeing it. So yeah, I think we're free to go on.
All right, good. All right, so this last example is it's the category of a non-obvious application. So there's a government we're working with in the Midwest, and it's a decision support scenario for child welfare. So let me quickly explain how this works. Okay, so I'm going to switch tabs here. The child welfare system works like this. If a child is in foster care or in state custody, the state will send a welfare worker a couple times a month to document the conditions of the child, make sure he's being properly cared for, and they write longhand notes, okay? And they get training in how to write these notes. And what you have on the screen in front of you is a representative note. It's fictitious, okay, but it is actually very representative. It's used for training child welfare workers. So you got a case here of Sandy, who was removed from her home by Child Protective Services and placed in foster care, and now the child welfare worker is visiting and documenting the conditions. And the way it works is every visit generates one of these reports. These are collected into a case file. And then at certain points in the year, there's someone in central administration who has to sit down and make a decision that will affect the trajectory of this child through the child welfare system. And the determination is made on the information in the case notes, but it's easy to miss information in the case notes. And when information is missed, sometimes the results can be catastrophic for the child. So they really wanted to get the error rate down because it happens a lot. People overlook some key piece of information. So what we did here is we took just this one case note and we loaded it into our platform. Okay, and I'm going to switch now to the platform, and this is Sandy's case notes. This is the corpus where it just literally contains that one case note. And now just imagine with me for a second that you're now the caseworker sitting in the central administrator, sitting in the central office, trying to decide, what needs to happen with Sandy. Is she fine with this family? Can she go back to her mother? So let's say first and foremost, I'm interested in physical abuse. Okay, so I'm going to put that into the search. Okay, and imagine that I'm not putting it into the search, but it's being proactively retrieved from the notes for me. So I can see anything related to physical abuse. It shows up on the screen, and then I make the decision. Was there physical abuse? Yes or no? And I've got this information on the side. Okay, so Sandy was removed from her home by Child Protective Services and placed in foster care after a teacher observed multiple bruises on Sandy's body. Mother claimed she was unaware of injuries. Sandy said mother's boyfriend often hit her for no reason. Okay, all connected to physical abuse, scattered throughout the document, but a semantic search system is able to go and retrieve all of these and kind of bring them to my attention, even though there's no keyword overlap. Physical and abuse don't appear anywhere in these sentences. If I change physical abuse to substance abuse, that would be another thing that someone would be interested in. Mother has a history of reported drug and alcohol use and was intoxicated at the time of the investigation. Caseworker explored the frequency and quantity of her alcohol consumption. I like this one here. Mrs. White stated she'd been drinking 2 or 3 cans of beer a day with friends. So beer, alcohol consumption, drug use, all of these are connected to the idea of substance abuse, but the substance abuse term itself is never explicitly mentioned in any of these sentences. So you can see the potential for neural information retrieval to pull back really relevant information, information that if you miss it could have a very high cost in the life of that child potentially. But neural information retrieval will catch it where a keyword system would miss it. And this is an example where you can enhance a decision-making system or decision support system using these kinds of technologies. So, I mean, this technology is very powerful. It's very broadly applicable, but it's also very, very new. Outside of the FANG group of companies, very few other companies even know about these capabilities, much less, have started to deploy them. But I think that with these cloud platforms now becoming available, in the next 2 to 3 years, you should see, widespread penetration of this technology in the industry. So we would just leave it there, and I'm available for any questions now or afterwards.